The purpose of this lab was to use the tracker program to observe the motion of an object in constant motion. The results were compared both observationally and mathematically to a computational model of the motion with the same initial data as the observed model. The fundamental principles involved in this lab were derived from Newton's second law. These are the two main forms of the equations that we will use. The first equation was derived from the definition of momentum, which states that the change in momentum over time is going to be equal to the net force. Also, this equation can be derived from the definition of acceleration. Acceleration equals the net force divided by mass, which is equal to the change in velocity over time. The position update formula, the second equation, is derived from the notion that the change in position over the change in time will equal velocity, where the v average can be calculated using the previous equation. Here is the tracker program's model. As the object moves across the floor, we can see that it's moving in the negative x-axis direction. If we had flipped the axes here, and the ball would be moving in the positive x direction, then the graph would show the motion and the position of the ball increasing towards the first quadrant as time goes on. This is the predicted motion, or the computational model that we created. The motion seen in the computational model is very similar to our observed model. The graph shows that the position as time increases is going in the negative x direction down towards the fourth quadrant, and that the motion of the ball goes left. This is a visual comparison of our two methods. The red is the predicted computational model motion, and the blue is the observed motion. Our initial observations is that the predicted motion is straight. By simple observation and our previous knowledge, we can assume that there is constant velocity. In our observed motion, it's straight at first, but then at a point it slowly starts curving, so we know that there's non-constant velocity throughout the motion. The curve shows that the ball is decreasing in velocity. As time goes on, the gap between the observed motion and the predicted motion is increasing. Now, going back to the fundamental principles involved, we're going to use these two equations to prove our observations. Going back to the fundamental principles involved, I'm going to use these two equations to prove my initial observations. The predicted motion is straight because the computer model kept the motion at F net equals 0. We know for a fact that throughout the entire motion, the net force acting on the ball is 0. The observed motion curves because the force that was negligible before increases enough to make an observable difference. Throughout the entire time, the F net didn't necessarily equal 0. Only at this point did it become big enough that we could observe it in the graph. The force continues to act on the object, making the gap between the computational model's motion and the observed motion bigger and bigger as the ball slows down. Now, this is our mathematical proof of the predicted motion's observations. Because the F net was kept at 0, when we use Newton's second law and calculate it, we can see that the final velocity always equals the initial velocity. This means that the average velocity that we use in the position change equation is going to be the same every single time, which means that the position will be updated and changed at a constant rate. The observed motion curves because the force was negligible before, so it didn't really make an observable difference until it hit this point. So if we plug it into the equation, we can see that until this point, we can safely assume that, similar to the computational model, that the final velocity equals the initial velocity, and that the position will update and change at a constant rate. But when we get to this point, the F-net is big enough that it makes a noticeable difference. The final velocity will be less than the initial velocity because as the velocity keeps updating, the net force is still going to be in play. So, the position is going to change at a non-constant rate because the average velocity will continue to decrease, which can be shown here. Now we can guess which forces come into play to cause the ball to slow down, but for now we don't know for sure, or how much all of these forces contributed. We only know that this is what the motion looks like.